So we have two remaining fancy types of ligands that we're going to discuss. I guess I shouldn't necessarily say ligands, but more about fancy things we have to deal with when it comes to electron counting. The first is going to be bridging ligands. So let's look at this complex that's an aluminum complex. That has a bunch of chlorines involved. It actually has two metal centers, two different alumina. And if I were to ask you to think about, right, what is our electron counting here? What are all of these ligands? It might be a little bit tough to figure out what to do with the middle, right? This is kind of a conundrum, right? What on earth do we do here? I'll put a big question mark. So these chlorides are what we call bridging ligands. Because they're bridging two different metal centers. And this gets the label, just like hapticity had that label eta. For bridging, we have mu. And the subscript denotes the number of metals that the particular atom is bound to. So if I was going to try to write out an abbreviation for this structure, I could call this mu2 chloride, aluminum 2, Cl2. Right, so this label here on the left is describing that bridging behavior for my chloride. And when it comes to electron counting, bridging ligands can be tricky. They can be very challenging to deal with, and this is a good example of why our understanding of oxidation states might be a little bit limited. So what I'm going to do is, normally these have an element of symmetry to them that we're going to use to our advantage. So when it comes specifically to these chloride cases, I'm going to treat this, as far as electron counting goes, as two separate aluminum complexes, right? And this isn't a perfect picture, but again, electron counting is just a formalism that allows us to understand structure. Electron counting doesn't have any basis in physical reality. And so if I draw this structure out right now, these look like X-type ligands. Right? We've looked at halogens, we've looked at chlorides already in our kind of ligand typing, and these look like X-type ligands. I should say, let me move this arrow over, right? It looks like an X-type there. But now if I imagine that these chlorines had all of their lone pairs, now I could imagine that maybe these other bonds that are occurring look a lot more L-type. Right? We have a 1 electron donor and a 2 electron donor here. So by drawing out this picture, we could say that each of our bridging chlorines, right? So each bridging chlorine is kind of like an X ligand and an L ligand, right? It's kind of like an X ligand and an L ligand. And so this is where kind of the oxidation state stuff gets messy. Technically, both of these alumina would be considered 3 plus for their oxidation state because they have these outer chlorines or chlorides that definitely contribute to the oxidation. And then we would kind of split the X-type ligand to each of the atoms or each of the metal centers as well. So each of these looks like an X and an L-type ligand, right? So really these are kind of like 3 electron donors, right? Using our kind of neutral method, these are 3 electron donors. And so with these halogens, halogens are probably the most common bridging ligand that we will see in 481 when we talk at least about bridging ligands. But we can generally split them down the middle and try to draw these out as if it's kind of leading you to say that one is kind of an X type interaction and one is an L type interaction. And again, these last few cases here are really where we kind of highlight the limitations of electron counting, right? So how would we do this, right? How would we go about counting the electrons for this particular? All right, so if we're going to do the electron counting here, right, I've already kind of written it out, so we can catch up a little bit here. But I've described these two different ligands, right? The bridging ligand as interacting like an X-type ligand, and one is like an L-type ligand to any of my alumina centers. And so if I'm going to count up my total number of electrons here, sorry, math is sometimes a little bit tricky. If I'm to count up my total number of electrons here, I can see that I would end up with 8 electrons for my alumina. I have two that are kind of my traditional X-type ligands. I have the one pink X-type ligand that's my bridging chloride, that's a 1 electron donor, and I have my L-type ligand that is giving these 2 electrons. And so I end up with a total of 8 electrons. If we look at aluminum on the periodic table, right, it's in the third row, so we aren't dealing with d electrons yet, so we aren't looking to get to 18. We're still looking to get to 8. So this is a way that we can count up these electrons in our system. This would technically make these aluminum 3 plus for the oxidation state because there's 3 X-type ligand interactions in each one, or for each of my aluminum centers. So this is how we can do electron counting for our bridging ligands. It's a little bit tricky to determine, right, the types of bonding that these are following, but again, we can try to kind of work our way through it the best that we can.